Hey guys, hello everyone. Welcome to Rasayan Academy, all of you. So I know that your examination for CSIRNet is on 18th of November and you are solving all the good previous year questions. So that is why I want you all for the last minute to go through these questions which were asked in the 30th November 2020 paper. So there were two papers in 2020. One of them was conducted on 26th of November and the other one was on 30th of November, right? So I've already made a video on this. You can check out in my profile, and I want you all to see the less popular questions of 30th November paper also of the CSI NET examination. So in this video, we'll be discussing about the important organic chemistry questions, not only name reaction, but yeah, simple questions also. All right, all of the important questions of organic. Right, so this is the first question that I've taken from this paper. I just want you all to try to solve these questions by yourself. Okay, so let's start, guys. This is our first question. The major product formed in the following reaction is, so as you can see over here guys, you have an alkene and you have H2SO4 and the amine is a secondary amine, right? So what do you think can happen in this reaction, right? Well, let's look at the options. So looking at the option number one, you see that the cyclization has happened and looks like the benzene has attacked, just like it would do in a substitution reaction like this. All right, so something like that has happened. But in option number one, electrophilic aromatic substitution, let's say acid catalyzed electrophilic aromatic substitution. In option number one, benzene attacks over here, which means that if you are first step, right, the acid base reaction is always the faster. So first of all, this electrophile is going to take the proton. Okay, so you can see guys, whenever I explain a question, but first try to do this question by yourself so that you yourself have a point of view of about that question, and then only you see the solution. Otherwise, if you just start looking at my answer, you will never be able to think of what is happening in this question, right? So that is very very important, right? What is the point of view that you should have about this question is that I'm having an alkene, and first of all, the alkene is going to take a proton. So, which position the alkene is going to take a proton? Absolutely the one that gives you a more stable carbocation, right? So, yes, the carbocation should form on this carbon, on the central 3-degree carbon, right over here. All right, and if that happens, the benzene must attack on this carbon, right? But in option number one, we see that it has attacked on the terminal carbon, this one. So option number one cannot be correct. Now moving onwards to option number two. If the benzene is doing electrophilic aromatic substitution and it attacks on this carbon, then it is going to have two methyls on the carbon which has attached to the benzene, and it is going to form how many membered ring? 1, 2, 3, 4, 5, 6 and 7 membered ring it is going to form. This is absolutely what is taking place. So we can say 2 could be correct. Now let's move onwards and see other questions, guys. Other option. In the other option, you see that it is making very less sense. Why? Because the nitrogen, when it attacks on this carbon which has actually formed a carbocation, it's going to form a very small ring, and that also spiro small ring. This is not possible. And also, if the carbocation forms on this carbon, which is actually not going to happen, if the carbocation forms over here and the proton is taken over here, then you get this product, which is absolutely not possible because you don't get a primary carbocation, right? So the answer is option number two, and the reaction is very simple. You first of all have to form a more stable carbocation, then the benzene does the electrophilic aromatic substitution. Next question, guys. Question number two from the same paper. The compound that answers both haloform and tolerant test. Yeah, just look at the question, all the options by yourself, and then we will discuss. So the compound that answers haloform, for what do you require for the haloform test? You require COCH3. You require this group actually. All right. But sometimes in the molecule COCH3 is not given. Sometimes the alcohol, the secondary alcohol and the CH3 is also given. So within the medium, within the haloform reaction medium only, it could be oxidized like this by taking away a proton from here. It can be oxidized, and both of these groups are going to give you the reaction. All right, an acyl group and a secondary alcohol, both of them, which has 3 hydrogen on the alpha carbon. That's important. Tolerance test is given by the aldehydes basically, which can be converted into COOH by the tolerance reagent. I just hope that you remember tolerance reagent, ammoniacal silver nitrate. So what's going to happen, guys? You are having ammoniacal silver salt that is going to be working as a very mild oxidizing agent to convert the CHO into COOH, right? So you're first of all going to eliminate this option. Why? Because this option already has a COH. I know that you are looking over here also that it has COCH3, which qualifies for this haloform but does not qualify for tolerance. The group is already oxidized. Similarly, this is an ester. This is already oxidized, does not qualify for both of them. This group also, guys, you are having only CH2 over here. Alright, on this carbon, adjacent carbon, you have only CH2. Does not qualify for haloform, although it qualifies for tolerance. Look at option number 3. You have one CH3 group adjacent to this CHOH, right? So I told you that it is going to get oxidized in the medium and it will give you the acyl group for the haloform test. What is the haloform test, guys? Haloform reaction is very simple. In the presence of a base like OH minus ya methoxy, in the presence of a base like this, the protons over here, these protons are removed and you are just having bromination. But since the reaction takes place in the presence of a base, continuous bromination, continuous enolate formation takes place, and you are getting all the hydrogen substituted. Now the next OH minus does not have a proton to remove, that's why it is going to attack over the carbonyl, and CBr3 minus eliminates. You are having COOH plus CBr3 minus. That minus is going to take a proton. Here you get the bromoform. So this is the haloform test. All right, and this requires this group, this particular group. All right, and it also qualifies for the tolerance test, which requires CHO. Once again, very simple question. Answer is 3. Question number 3 now. The major product formed in the following reaction is. So once again, what is your point of view regarding this question? Try to solve it. Right. So you see that there is a base, all right, and there is a electrophile, right? So the question is asking you that from which position the base is going to occupy a proton. This is one position where there are protons next to the carbonyl enolate can form. This is another position where acidic protons are present because there is conjugation on this side and absolutely there is an ester on this side. Also, this methyl is also going to be a little bit acidic because of the extended conjugation that you have. Now the question is, where is the proton being removed? And the further question is, which position on this electrophile is being attacked, this position or this position? Okay, so that both of these are important. First thing, guys, this hydrogen is going to be less acidic as compared to this hydrogen. Why? Because this is a ketone. If it was a simple ketone, then you would remove this proton first, but then this is a substituted ketone like this. All right, it's a conjugated ketone. So you cannot say that this hydrogen is more acidic, not at all. You can say this hydrogen is less acidic than this hydrogen, or ये तो definitely less acidic है because it's a methyl group. So the only condition that we can think of right now is to remove this proton which is next to the ester and also next to the unsaturated group. And if we do so, if we let's say do this question like this, then what happens, guys? Yes, then what is going to happen if we do the reaction like this? Alkylation will take place. Where is the alkylation going to take place? Now that's also a good question, because is it going to take place directly Can we directly do the attack over here? See, in this molecule, the more favored attack is directly on the carbon because it is a less substituted carbon. It's a primary halide. So 1 degree halide is going to just give you the direct attack, right? So attack will be over here, not over here, right? So that's okay. But the question is asking once again, the negative charge can do a direct attack on this position, or it can also do a conjugate attack, which is going to basically lead to the product formation from this carbon. So that's up to you guys. What do you decide? In option number 2, we will see that a direct addition is not done from this carbon. See, in option number 1, a direct addition is done, which is actually a little bit more hindered possibility. And in option number 2, the negative charge conjugates and goes on to this carbon. Why does that happen, guys? Why does the negative charge conjugate? That is our question. Why does it delocalize? Because when the negative charge delocalizes, we have the stability in the enolate formation. We have the negative charge going to the oxygen like this. Alright, let's say the negative charge is resonating into the oxygen. Right, and when the oxygen bond falls back like this, then absolutely from this carbon the attack is going to take place. From this carbon exactly. So that's why your answer is option number 2, and the attack is going to take place from this position particularly. So you'll ask me that the position of the double bond is different, isn't it? Yes, the position of the double bond is different. Look at it. Yeah, don't forget a methyl also. The position of the double bond is like this, and you are doing your attack in this way, right? How does it change, guys? Right, the position of the double bond can change because now there is one more enolizable proton which can be lost in this way, and finally, yes, and finally when there is aqueous workup, you are going to get the carbonyl once again, and the double bond falls over here, and this is going to be like this. Okay, so the conjugation, the extended conjugation is going to help in the tautomerization, and the change in the position of the double bond takes place due to isomerization. Alright, so answer is option number 2. Very, very important. This hydrogen is not acidic, and obviously the methyl hydrogen is absolutely least acidic. Okay, so this proton is removed, but the attack is taking place over here because of conjugation. Very, very important. Next good question, guys. The most efficient reaction in the term of atom economy among the following is? Yes, so this is our fourth question. Atom economy, when we are looking at, guys, we are not going to see the whole mechanism. Atom economy, we will just count the number of electrons, count the number of atoms. Yes, count the atoms in the reactant and the product side. Okay, because if there is no loss of the number of atoms, then obviously it is 100% efficient, theoretically at least. Yes, now look at this, guys. PHCHO, CH3MgBr. So definitely CH3 minus is attacking over here. You are having OH molecule. This is the molecule, right? But in the next step, you have aqueous workup that's going to take away a proton. And what about the MgBr? Where does it go? Got wasted, right? So MgOHBr, that got wasted, right? So that is why this is not the most efficient reaction at all. Grubbs catalyst. Grubbs catalyst is used, and it is going to do the alkene metathesis over here, ring closing metathesis reaction, and along with that you are going to get a ethene. So what about this ethene? There is no record in the question. Alright, so this ethene is getting wasted, and the major molecule is having 2 carbons less. So both of these are absolutely not correct. Look at option number 3, guys. Just count the number of carbonyls and the OHs. You have 2 carbonyls over here, you have 2 carbonyls in the product, you're having 1 OH, this is 1 oxygen, and this is 1 hydrogen, and you are having 2 methyls over here. These are your 2 methyls. Okay, 1 ethyl group as it is. What next? You have 1 carbon, alright, and this tertiary butyl group. So this is as it is, guys, the nitrogen and the tertiary butyl group. So this is the most efficient reaction, most efficient as compared to all the others, most efficient. And what about this? ये देखो CHO OH OH. What will happen? A loss of water molecule is going to happen. So then only you are going to get this product. So once again, not the most efficient. 3 is our correct answer. Number of atoms should be there should be very less difference in the number of atoms in the reactant product. Then we say it is most efficient reaction. Question number 5. You look at this, guys. Major product formed in the following reaction is. Okay. So in this question, once again, I'll ask you, what is your viewpoint? How does the mechanism go through? That is the question. In the presence of LDA in the first step, how does the reaction proceed? First of all, guys, LDA is going to take away this proton and it is going to give you a benzyne. Just like this. You're going to get a benzyne just like this. After that, guys, there is a reduced selectivity issue. What is that issue of reduced selectivity? That is the the alkene is going to attack like this, or the alkene attacks like this, which is going to give you two major and minor products like this. So let's see, guys. Yes, we want to attack on the benzyne in such a way. So benzyne attack should take place on such a way that the ortho position becomes electron rich. Alright. So the negative charge must be close to the oxygen group. This is always stabilized because of the minus I effect. So that's why you can write that the negative charge once again attacks back on the carbonyl. Alright, so this is basically 1, 2, 3, 4, 4-membered ring. Okay, so basically, guys, what I've done is I've just once again removed one of the methoxys and only one of the methoxy remains. Now in the last step, it is going to be aqueous workup. In the last step, you are just going to hydrolyze this molecule. The excess of the methyl remains that is going to get eliminated and you are going to get this product. Alright, so depends on the reduced selectivity of how the reaction is going to proceed. This is the answer. Answer is option number 1. Okay. Alright, guys. So moving to the next question. The question is asking you major product formed in the following reactions. Now to this alkene which is given, it's a styrene molecule, right? So what's given? Formalin. What is formalin, guys? It is a polymer of the formaldehyde. It is a polymer of formaldehyde, formalin, and in the presence of acid, you can just consider that you are going to get the CH2OH protonated just like this, so that you are going to get a very electrophilic carbon over here, right? So if that is so, guys, if you are getting a very electrophilic carbon on this side, then what's going to happen? The double bond is going to attack in this way on the formalin या फिर formaldehyde molecule, and you are going to generate one CH2OH like this, and you have a positive charge. But are you going to have just cyclization just like this? Are you just going to have the OH attack over this carbon and the cyclization product maybe something like this? Option number 3, no. You're not going to have so. Why? Because you are having one more molecule of the formalin which can be attacked in this way like this. CH2, one more oxygen. This oxygen can attack over the positive charge over here and the proton could be lost. I'm just simply talking about the sigma skeleton structure. right? What the bond polarity describes, right? Definitely we can just try out the whole mechanism in the presence of H2SO4, who is going to take away the proton, water, definitely. So all these trivial things I'm not telling you, just the bond polarity is important. So answer is option number 4, and the molecule is simply going to be attacked like this. All right, so to a benzylic carbon, there is one oxygen connected in this way, which has a central CH2. So there is a central CH2 over here, just like this, and then CH2, CH2, and CH once again. All right, so yeah, this is how your answer is going to be. However, you have one more important thing over here. Let's see. You have yes, two carbons, two CH2, one over here, another over here. Yes, yes, the same. All right, so this is the correct answer, option number 4. Why the option number 2 is wrong? Because you cannot define that the attack is taking place exactly from this position. One CH2 over here and one CH2 over here, right? You cannot define that, isn't it? Right. So, yeah, it's a little bit different over here. 2 is not correct. See, when you're just following the simultaneous attack, you will just get this answer. That's it. Now, moving on to another important question. Now, this is the name reaction question, the sequence through which the following reaction proceeds. You are given the reactant as well as the product. What are you going to do in the presence of heat there? Seems like you are going to have a 3,3 sigmatropic possibility. It is the allyl vinyl ether system. All right, let's give the numbering 1, 2, and 3 over here, 1, 2, and 3 over here, right? So there is a possibility of 3,3 sigmatropic, and whenever you have the allyl vinyl ether system, you are going to do Claisen rearrangement. Absolutely, Claisen rearrangement. But guys, after the Claisen rearrangement, the molecule is going to look something like this. The molecule is going to look like this. Now, this is your allylic carbon once again. Okay, but there is no more possibility of further 3,3 sigma tropic reaction. Why? Because even if you are counting from here 1, 2, and 3, 1, 2, and 3, this whole group is not going to end up on nitrogen. Nitrogen is not going to favor the reaction, and also in the product, you don't have it on nitrogen, you have it on this carbon. So, how are you going to do it, guys? How are you going to proceed with this reaction? You might want to convert this Me to CH2H and see what is possible. Tautomerism is possible, but that involves the benzene ring as well. Tautomerism is possible, but it involves the benzene ring as well, and that is why the intermediate of the following step is going to look like this. You have one double bond here and here and here. Right, this is how the reaction, this is how the molecule looks like after tautomerism, which involves the benzene ring. Okay, so this is a very long way tautomerism. Now you have the same possibility co-prearrangement where all carbons are possible. All of the units are made of carbon. So this is 1,5-diene. For co-prearrangement, you require the 1,5-diene, and for the Claisen, you require the allyl vinyl system. So just do the rearrangement, guys. You are going to have this very simple molecule. In this way, the methyl is as it is, and here you are going to get connected the allylic group. So basically the answer is over here, and it doesn't matter if you put the 3 bonds in this ring or in this ring, both of the rings are aromatic. So answer is option number 1 to this question. Let's move onwards to next important question, guys. The major product formed in the following reaction sequence is, so just try this by yourself, guys. It's a very simple reaction. What do you see over here? You see that you're having an acid and you can convert it to acyl chloride. So first of all, let's convert the acid to acyl chloride in the presence of SOCl2. Alright, now the diazomethane, like this. CH2 minus N2 positive. This is the species. It is going to replace the chloride from here. Alright. it is going to replace the chloride from here, and you are having the carbonyl CH2N2 positive like this. Now, in the presence of another CH2N2 molecule, yes, guys, you are actually guessing it correct. It is the Arndt-Easter actually the Wolff rearrangement. But yes, the Arndt-Easter reaction is you are starting from a carboxylic acid and then moving onwards with the same reagents, right? Yes, so this is going to be CH minus N2 positive in this way. All right. So the nitrogen eliminates and you are going to end up with the acyl carbene. That acyl carbene might do a lot of reactions. So let's see guys what is possible. You are having an acyl carbene like this. So the acyl carbene can undergo rearrangement. Okay. See, if we try out this possibility, the acyl carbene can undergo, there's one carbon over here, this is another. So this carbon is migrating on to this carbon, alright, which has formed a double bond with the carbonyl in this way. Alright, so this is the molecule. And guys, since we are having light, we might try out 2 plus 2 cycloaddition. If we are doing the 2 plus 2 cycloaddition of the alkene over here and this alkene, what is going to be the product? The product is going to look something like this. Alright, so this was the double bond. Let's say this is the product. Alright, these two carbons are going to connect to these two in this way, and there is a carbonyl. So I know that it's very difficult to understand from here, but if you just try to visualize, if you just try to see what is the what is the number of ring that it forms. See, it's going to form a ring over here and one more ring over here, which is going to be a three-member ring. Looks like a three-member ring actually. This is one tricyclic carbon. This is another, and in between you're going to have this carbonyl. One tricyclic carbon, this is another, and it is a four-member ring itself. See, it is a four-member ring over here that you're forming, and same is the scenario, four-member ring you're forming. Answer is option number 3. Alright, so this is what you have to see over here. Third is the correct answer for this question. Now we move onwards. Another very important question, guys. Major product formed in the following reaction sequence is. You are seeing a very, very important question over here based on regio and chemoselectivity once again. So mostly regio selectivity. Now dicyclohexyl borohydride is going to make sure that you have the hydride, hydroboration in this way such that the boron stays on the less hindered side away from the N-butyl group. This is going to add in this way. Alright, and I just hope guys that you are doing it by yourself. Okay, always do the questions by yourself, right? So yes, so let's just write this butyl. This is a double bond now, H and boron dicyclohexyl unit. Right over here, this is another bromine. Okay, so yeah, this is what we see over here, guys. This is the molecule. This is the first step, hydroboration. Now, oxidation is not given. We are not having oxidation. This is acetic acid. All right, deuterated acetic acid. Now, when you are providing, there are there are 3 or 4 different reactions for the hydroboration. If you provide H2O2 and OH minus, that is going to give you the alcohol. If you are doing the acetic acid, that's going to give you the alkane. That's going to give you the alkane. So where is the deuterium going to add? That is the question. Yes, the acetate is going to attack over boron and the bond is going to fall over deuterium. So this is a stereospecific reaction, guys, without any doubt. The deuterium adds on the same carbon where there was boron. So boron was right over here, deuterium adds over here, hydrogen and deuterium are on the same side. Okay. So first step is hydroboration, which is thin addition. Hydroboration is thin addition. Along with that, boron always adds on the less hindered side, and the elimination will be in such a way that it's a stereospecific reaction on the same carbon deuterium is going to add. So answer is option number 1 to this one. Moving onwards, another important question, guys. This is super, super important. Birch reduction, chemoselectivity, major product formed in the following reaction. So first step may you are doing Birch reduction, and guys, Birch reduction of this question, or let's say similar question, has been asked in the gate examination previously. That is when you are transferring the electrons. Okay, in the Birch reduction, when you are transferring the electrons, let's say we transfer the electrons over here, and since there is a carboxylic acid group, which is a electron withdrawing group, it is happy to take the electrons. Alright, so electrons are being transferred onto this carbon and not over here. Why? This question is asking you the direction of the electron transfer. This is the direction of the electron transfer because of the electron withdrawing property of the carboxylate group. Alright, so this is how the electron transfers. Yes, and we are going to do the Birch reduction, guys. Sodium is going to transfer one more electron, then it becomes a negative charge, and then it is going to grab a hydrogen from the ammonia. So finally there is reduction on this carbon, but this carbon is stabilized like this because of the carboxylate. It is stabilized. So that is why when you are providing an electrophile in the next step, what is the electrophile? CH2, CH2, CH double bond CH2. Now this is the electrophile. When it is provided, you are going to have something like this. Alright, acha sorry, O minus is not going to attack. Absolutely it won't. Yes, it is going to fall back over here and this carbon is going to attack. So be very, very careful in drawing these products. It is so important, guys. Always this carbon is going to do the attack like this, and this is the product. Okay, this must be the product, which is option number 2. Very, very important. Not on the side carbon, not over here. Absolutely doesn't make sense, and not exactly on the methyl carbon. Never. So only 2 is the correct answer. We move onwards to next question. Major product formed in the following reaction sequences. Now this question was also asked previously in the gate examination. You are doing acylation of furan. So furan is not that aromatic, and acylation is already making it electron deficient, right? So yeah, the first electrophilic aromatic substitution, acylation, will definitely take place on the 2 or the 5 position like this. Yeah, this is your product of the first step. What happens in the next step? Next step is nitration. And guys, in the previous gate examination, you said you got the correct answer as somewhat like this. The nitro is going to add on the meta position. Alright, why is that so? Because it is considered that the acyl group is electron withdrawing in nature. It is making the whole ring electron deficient. That's why the fifth position is no more electron rich. So it was considered कि ये major product होगा. लेकिन यहाँ तो ये option ही नहीं है. You don't have this option that this is on the second position and this nitro is third. Nitro does not add first. The acyl adds first, so this has to be on the 2. ये नहीं है, so this is wrong. This is also wrong. Both of them 3 and 4 absolutely wrong. This is 2, but this is exactly close to it when the fifth position is empty. Absolutely wrong. So the only correct possibility is option number 2. So we have to see according to the question how are we going to answer. Just check out this question in your gate previous examination question as well. You're going to get this and you'll understand what I'm trying to say based on the options we are going to do. So when this kind of an option is not present, so you are just going to write that the maximum possibility then remains to this. So this is your correct answer, option number 2. Okay. Question number 99. Actually, I've just taken the question from the paper directly. Yes. Major product formed in the following reaction sequence. Another beautiful question, guys, and such good easy questions on selectivity, just selectivity. Yeah, look at this. You are having the silyl ether. You are having silyl ether, you are having an iminium ion over here, you are having an iminium ion like this. Okay, so what is going to happen? There is I minus, right? So I minus can actually attack over silicon, and let's say chalo theek hai, it's not attacking over silicon. I am just using the oxygen to donate the electrons. Yeah, there's a reason for that. I'm just using the oxygen to donate the electrons and attack over this carbon. You have a one double bond O, SiMe3. Oxygen has a positive charge. And this is one positive double bond, and this is CH2NMe2. Why have I written this product? Yeah, why couldn't I just add this CH to somewhere else? Let's say I could have added over here. Yes, isn't it? Now that makes option number 2. I could have added it over here, right? But why is it wrong? Absolutely wrong, because when there is one more double bond in conjugation, we are just not going to stop midway. We are going to go all the way long till here, right? Yes. Now, also this is a less hindered position. So this is wrong. And getting the CH3 over, CH2 over here is also wrong. So we are going to move onwards, and we might think of 3 or 4. Yes. Now what happens is, in the next step, CH3I and then NaOH. So CH3I means methyl iodide, means that your nitrogen is going to grab one more methyl group, and it is going to look something like this. CH2NMe3 positive. Yes, you're going to see that this is your molecule. Then NaOH means you are going to remove the SiMe3 in this way, and also NaOH is used for the removal of a proton from here, and even E2 elimination. It is used for E2 elimination reaction OH minus. Alright, I think the silicon is going to be removed by the iodide only, because that is present in the first step. It has to be removed in the first step only, right? So yeah, this will be free in the first step, right? Yeah. And OH minus is only used for E2 elimination. That is going to give you this product, option number 3. Okay. So yes, guys, this is so important. The video is very, very important for everyone. I just hope that you have seen it properly, and this just share it with your friends at the last moment. They are not going to hamper you. These are very easy questions, and I will see you guys in more videos, more content we are going to study. Take care of yourselves, guys, and all the best to all of you.